1943, Supermarine Aviation Works, Southampton. The Rolls-Royce Griffin engine had just transformed the legendary Spitfire into an uncontrollable beast. Nearly 2,000 horsepower of raw fury that twisted the aircraft like a cork in a bottle, making pilots fight the stick just to fly straight. Every engineer in Britain knew the solution had to be simple, proven, reliable. Robert Harrison had a different idea. Twin propellers spinning in opposite directions on the same shaft. His own colleagues called it stupid, a mechanical nightmare, too heavy, too complex, too fragile for combat. The Ministry of Aircraft Production wanted nothing to do with Harrison's contraption. But when that first modified Spitfire lifted off the runway and hit 470 miles per hour without a single wobble, when test pilots reported handling so smooth they could thread a needle in a dogfight, suddenly, everyone wanted to know how an engineer's stupidest idea became the Allies' most deadly secret. The autumn rain of 1943 drummed against the hangar roof at Supermarine Aviation Works, each drop marking time that Britain couldn't afford to lose. Inside, beneath the harsh glare of industrial lighting, mechanics worked frantically around the sleek fuselage of what should have been the Royal Air Force's most formidable weapon. The Spitfire Mark 21 represented everything the Allies needed: speed, firepower, and the legendary agility that had saved Britain during the darkest days of the Blitz. But something had gone catastrophically wrong. Squadron leader Thomas Crawford pulled himself from the cockpit, his flight suit soaked with sweat despite the October chill. His hands trembled slightly as he removed his leather gloves, not from fear, but from the sheer physical exhaustion of wrestling 2,000 horsepower of barely controlled fury through the Hampshire sky. The new Rolls-Royce Griffin engine had transformed his beloved Spitfire into something that felt more like riding a bucking horse than flying an aircraft. "How bad?" asked Chief Engineer Edward Bennett, already reading the answer in Crawford's expression. "At 350 miles per hour, she wants to roll left so hard I nearly put her into a spin," Crawford replied, his Scottish accent thick with frustration. "The torque from that bloody great engine. It's like the propeller is trying to tear the nose clean off the airframe above 400 miles per hour. Forget about it. No pilot alive could hold her straight in a combat situation." The numbers painted a grim picture. The Griffin 65 engine generated 1850 horsepower at sea level, nearly double that of the original Merlin engine that had powered earlier Spitfire variants. That raw power should have pushed the aircraft past 470 miles per hour, making it faster than any German fighter in the sky. Instead, the massive torque reaction, the equal and opposite force Newton had described centuries earlier, twisted the entire airframe with such violence that pilots couldn't maintain level flight at combat speeds. Bennett ran his hand along the propeller hub, feeling the slight vibration that never fully stopped, even when the engine was shut down. The engineering challenge was brutally simple in concept, devastatingly complex in execution. Every revolution of that massive four-bladed propeller generated a rotational force that tried to spin the aircraft in the opposite direction. At low speeds, pilots could compensate with rudder input and muscle. But as air speed increased, the aerodynamic forces amplified the problem exponentially. The result was an aircraft that became progressively more dangerous to fly the faster it went. Exactly the opposite of what combat demanded. "The Germans have the same problem with their high-powered fighters," Bennett said, though his tone carried no comfort. "Their Folly Wolf 190 series suffers from similar torque issues, but they've learned to work around it with pilot training and tactical limitations." Crawford shook his head sharply. "We can't work around physics, Edward. This isn't about pilot technique or training protocols. At the speeds we need to achieve air superiority over Western Europe, this aircraft is simply unflyable. And if we can't solve it," he didn't need to finish the sentence. Everyone in that hangar understood the stakes. The Ministry of Aircraft Production had already invested millions of pounds developing the Griffin engine and redesigning the Spitfire's airframe to accommodate its increased size and weight. Production schedules called for hundreds of these aircraft to begin rolling off assembly lines within months. The Royal Navy desperately needed the naval variant, the Seafire, to match the performance of American carrier-based fighters in the Pacific theater. Failure wasn't just an engineering setback. It represented a potentially catastrophic gap in Allied air power at the most critical phase of the war. 15 miles away in the cluttered office of Roll Air Screws Limited, Robert Harrison sat surrounded by technical drawings, slide rules, and empty teacups. The chief designer had spent the past week analyzing flight test data from the troubled Spitfire, searching for a solution that his colleagues increasingly believed didn't exist. The conventional approaches had all failed. Increasing rudder size added weight and drag without solving the fundamental problem. Modifying the engine mount to reduce torque transmission weakened the airframe structure. Adjusting propeller blade angles helped marginally, but created new problems with efficiency and vibration. Harrison's reputation within the aviation industry was complicated. At 42, he possessed an intuitive understanding of aerodynamics that bordered on genius, but his solutions often struck more conservative engineers as needlessly complex or impractical. He had designed propeller systems for Rolls-Royce that pushed the boundaries of what manufacturing technology could achieve, earning grudging respect for their performance and equally vocal criticism for their production challenges. His colleagues at Rawtall had learned to expect the unexpected from Harrison, though few were prepared for what he proposed that gray October afternoon. The concept emerged from Harrison's understanding of torque as a fundamental force rather than a problem to be suppressed. Instead of fighting the Griffin engine's massive rotational energy, he proposed harnessing it through a contra-rotating propeller system. Two propellers mounted on the same shaft, but spinning in opposite directions would cancel out each other's torque reaction while delivering unprecedented thrust efficiency. The engineering challenges were staggering. The system would require a complex gearbox to drive both propellers from a single engine output, adding weight and mechanical complexity to an aircraft already pushing the limits of structural design. The contra-rotating propellers would need to be precisely balanced to prevent catastrophic vibrations, and the entire assembly would have to withstand the enormous stresses of combat maneuvering. Most critically, the system would have to be reliable enough for mass production and field maintenance under wartime conditions. When Harrison first presented his drawings to the ROL engineering team, the response was immediate and overwhelmingly negative. Senior engineer Philip Thompson called it a mechanical Rube Goldberg contraption that would be impossible to manufacture in quantity. Production manager George Davies worried about the weight penalty and maintenance requirements. Test engineer Andrew Mitchell questioned whether the system could survive the stresses of carrier operations for the Naval Seafire variant. It's simply too complex, Thompson argued during a heated meeting in Harrison's office. We're talking about essentially building two complete propeller systems and somehow making them work together perfectly. The gear ratios alone will require precision manufacturing that we can barely achieve under PCM conditions, let alone with wartime production pressures. But Harrison had done his calculations. The contra-rotating system would indeed be heavier than a conventional single propeller, roughly 200 pounds more, but the elimination of torque reaction would allow the aircraft to achieve its full speed potential. More importantly, the improved propeller efficiency would actually increase thrust by nearly 15%, more than compensating for the additional weight. The Spitfire Mark 21 could finally become the 470 miles per hour interceptor that the Royal Air Force desperately needed. As autumn deepened into winter, the debate over Harrison's stupid propeller design would determine not just the fate of Britain's most famous fighter aircraft, but the balance of air power over the battlefields of Europe and the Pacific. The Ministry of Aircraft Production's boardroom in London felt more like a tribunal than an engineering conference when Harrison arrived on the morning of November 15, 1943. Around the mahogany table sat some of Britain's most senior aviation officials, their faces bearing the weight of a war that had already consumed 4 years and showed no signs of ending quickly. Air Marshal Sir Christopher Reynolds presided over the meeting with the grim efficiency of a man who had watched too many promising aircraft designs fail when they were needed most. "Mr. Harrison," Reynolds began, his voice carrying the clipped authority of the Royal Air Force. "We've reviewed your proposal for this contra-rotating propeller system. I must say, the initial reaction from our technical staff has been skeptical." He gestured to a stack of reports that seemed to tower over Harrison's modest folder of drawings. The consensus appears to be that your design introduces unnecessary complexity at precisely the moment when we need proven, reliable solutions. Harrison had expected this resistance, but the formal setting made his throat tighten with nervous energy. These men controlled the fate of British aviation, and their decision would determine whether his months of calculations and sleepless nights had any meaning beyond academic exercise. Sir, with respect, I believe the complexity of the system is precisely what makes it effective. We're not simply adding components. We're fundamentally solving the torque problem that has made the Griffin engine unusable at combat speeds. Director of Technical Development, Sir Martin Hughes leaned forward, his reputation as one of Britain's most accomplished engine designers, lending weight to his skepticism. Mr. Harrison, your proposal calls for a gearbox system that would make this propeller assembly the most complex ever fitted to a fighter aircraft. We're talking about contra-rotating shafts, planetary gear reduction, and precision timing that must remain perfect under combat conditions. The maintenance requirements alone could ground entire squadrons. The numbers Harrison had prepared told a different story, but he knew that raw data wouldn't be enough to overcome institutional inertia. The gearbox complexity is manageable with proper manufacturing tolerances. De Havilland has already proven that complex propeller systems can be mass-produced with their variable pitch mechanisms. Our system would use a two-stage planetary gear train with a reduction ratio of 0.77 to 1 for the forward propeller and 0.62 to 1 for the rear. The differential rotation speeds would be precisely calculated to cancel torque while maximizing thrust efficiency. Group Captain William Ashford, representing operational requirements, shuffled through a folder of combat reports for Mediterranean and Pacific theaters. Even if your system works mechanically, Mr. Harrison, we're concerned about weight and balance. The Mark 21 is already heavier than previous Spitfire variants. Adding 200 pounds of additional propeller machinery could affect performance in ways we don't fully understand. Harrison had anticipated this objection and pulled out his most carefully prepared calculations. The weight penalty is real, sir, but the performance gains more than compensate. Our estimates show a thrust increase of 15% combined with complete elimination of torque reaction. The aircraft would not only achieve its design speed of 470 miles per hour, but maintain controllable flight characteristics throughout the entire speed range. Current test flights show the Mark 21 becoming increasingly dangerous above 350 miles per hour. Our system would extend safe operation well beyond 400. What Harrison didn't mention was the mounting pressure from intelligence reports about German aircraft development. Ultra-intercepts had revealed that Messid was developing high-speed variants of their Mi-262 jet fighter, while Fall-Wolf continued refining their high-altitude TA-152 series. The Allies needed every possible advantage in air speed and maneuverability to maintain air superiority over Western Europe during the anticipated invasion. Reynolds consulted his notes, clearly weighing the technical risks against operational necessities. Your proposal would require significant modifications to existing production lines. How long would it take to develop a working prototype, assuming we authorize the project? 6 weeks for the initial gearbox design and manufacturing, sir. Another 4 weeks for propeller fabrication and balancing. We could have a test installation ready for flight trials by early February. Harrison's confidence masked the enormous technical challenges involved. The contra-rotating system would require precision engineering that pushed British manufacturing capabilities to their limits. Each propeller would need to be individually balanced to tolerances measured in fractions of ounces. While the gearbox would demand gear-cutting accuracy normally reserved for marine chronometers, the room fell silent as the officials absorbed the timeline. 6 months had passed since the first troubled flight tests of the Griffin-powered Mark 21, and pressure from operational squadrons was mounting. Pilots were demanding aircraft that could match or exceed the performance of German fighters, particularly at high altitudes where the Griffin engine's power advantage should have been decisive. Air Commodore Henry Palmer, who had overseen fighter development throughout the Battle of Britain, finally broke the silence. Mr. Harrison, your reputation suggests that when you propose something this unconventional, it's worth serious consideration. But I must ask directly, Are you absolutely certain this system will work? We cannot afford another failed modification program. Harrison met Palmer's gaze directly. Sir, I stake my career on it. The physics are sound, the engineering is achievable, and the performance gains are exactly what the Royal Air Force needs. The Spitfire Mark 21 with contra-rotating propellers will be the fastest, most maneuverable fighter aircraft in the world. The bold statement hung in the air like a challenge. Reynolds exchanged glances with his colleagues, recognizing that Harrison's confidence carried the weight of genuine technical expertise. The man had designed propeller systems for some of Britain's most successful aircraft, and his track record suggested that his unconventional solutions often succeeded where traditional approaches failed. Very well, Reynolds said finally. We'll authorize a limited development program, one prototype installation, full flight testing, and complete performance evaluation. But understand, Mr. Harrison, if this system fails, or if it delays Mark 21 production by even a month, the consequences will extend far beyond your career. As Harrison gathered his papers and prepared to leave, he felt the weight of responsibility settling on his shoulders like a lead blanket. The next few months would determine whether his stupid design would revolutionize fighter aviation or become another cautionary tale about the dangers of engineering hubris. Either way, the Spitfire's legacy and possibly the outcome of air battles over Europe now depended on gears, shafts, and propellers spinning in directions that defied every conventional assumption about aircraft design. The war wouldn't wait for perfection, but it might just reward the kind of radical thinking that transformed impossible ideas into battlefield reality. The morning of February 23, 1944 dawned gray and bitter across the Salisbury Plain with winds gusting to 25 knots across the experimental airfield at Bosom Down. Inside Hangar 7, the modified Spitfire Mark 21 sat like a mechanical alien among its conventional siblings. The massive contra-rotating propeller assembly dominating its nose with an almost predatory presence. The twin propellers, each 11 feet in diameter, created a visual illusion that seemed to challenge the fundamental laws of aviation engineering. Test pilot squadron leader Marcus Sterling approached the aircraft with the careful attention of a man who understood that he was about to risk his life on an unproven theory. At 24, Sterling had already survived 3 years of combat flying over Britain, France, and Malta, accumulating nearly 800 hours in various Spitfire variants. His reputation for precise aircraft evaluation had earned him assignment to the most experimental programs, but nothing in his experience had prepared him for the mechanical complexity now mounted on the nose of Spitfire serial number RK958. The contra-rotating propeller system represented 6 months of intensive engineering by Harrison's team at ROL. The forward propeller rotated clockwise at 1,825 revolutions per minute, while the rear propeller spun counterclockwise at 1,475 revolutions per minute. Between them sat a gearbox weighing 193 pounds, machined to tolerances normally reserved for precision clockwork. Every component had been balanced within half an ounce, yet the entire assembly still vibrated with a frequency that seemed to pulse through the airframe like a mechanical heartbeat. Chief Test Engineer Victor Lawrence supervised the pre-flight inspection with nervous energy that infected everyone in the hangar. The gearbox temperatures stayed within normal ranges during ground running. He reported to Sterling, consulting a clipboard thick with data sheets. Oil pressure maintained 60 pounds per square inch throughout the power range. But Marcus, we're still seeing harmonic vibrations at 1,800 engine revolutions per minute that we can't fully explain. Sterling nodded, running his hand along the propeller hub assembly. The system looked impossibly complex compared to the elegant simplicity of conventional single-propeller installations. What's our planned test profile? Conservative approach, Lawrence replied. Climb to 8,000 feet level flight at varying power settings. Then gradual speed increases up to 400 miles per hour if the aircraft remains controllable. We're particularly interested in torque reaction characteristics and any unusual handling qualities. Harrison stood quietly near the aircraft's port wing, his face betraying none of the anxiety that had kept him awake for the past week. The morning represented the culmination of his professional career, but it also carried the potential for catastrophic failure that could end not only his reputation, but Sterling's life. Every calculation had been checked and rechecked, every component tested to destruction limits. Yet, aircraft design remained as much art as science. At precisely 9:15, Sterling strapped himself into the familiar cockpit of the Spitfire, though the instrument panel now included additional gauges for monitoring the complex propeller system. Engine oil temperature, gearbox oil pressure, forward propeller pitch, rear propeller pitch. Each parameter required constant attention during what should have been routine flight operations. The Rolls-Royce Griffin engine fired with its characteristic deep rumble, but the sound was immediately altered by the contra-rotating propellers into something entirely new. Instead of the familiar rhythmic pulse of a single propeller, the twin assemblies created a complex harmonic that seemed to vibrate through the pilot's bones. Ground control cleared Sterling for takeoff at 932, and he advanced the throttle with deliberate care. The Spitfire began its takeoff roll with surprising smoothness, the contra rotating and propellers eliminating the familiar left-turning tendency that every Spitfire pilot had learned to counteract with right rudder input. For the first time in months of testing, the Mark 21 tracked straight down the runway center line without constant pilot correction. Liftoff occurred at 85 miles per hour exactly as predicted, but Sterling immediately noticed something wrong. The aircraft felt sluggish in the climb, requiring more power than expected to maintain a reasonable rate of ascent. The additional weight of the propeller system was clearly affecting performance more severely than Harrison's calculations had suggested. By the time Sterling reached 5,000 feet, he was using nearly full throttle to maintain 2,000 feet per minute climb rate, performance that should have been easily achievable at 75% power. Boscom control. This is test 27, Sterling radioed. I'm experiencing higher than expected power requirements for normal climb performance. Requesting permission to level off at 6,000 feet for handling evaluation. The response crackled through his headphones immediately. Test 27. You're cleared to level flight. How does she handle? Sterling reduced power to cruising settings and was surprised by the aircraft's response. Despite the climb performance issues, the Spitfire felt remarkably stable in level flight. The elimination of torque reaction had transformed the aircraft's handling characteristics in ways that went far beyond simple directional control. The entire airframe seemed more solid, more predictable, as if the contra-rotating propellers had somehow tamed the wild energy of the Griffin engine. At 300 miles per hour, the aircraft that had previously tried to roll uncontrollably now flew with the steady precision of a much smaller, less powerful fighter. Sterling experimented with gentle turn, steep banks, and rapid direction changes, finding that the Mark 21 responded with an agility that seemed impossible for such a large, heavy aircraft. The elimination of torque reaction had restored the legendary Spitfire handling that had made the type famous during the Battle of Britain. But when Sterling advanced the throttle toward maximum power, the aircraft's performance became genuinely alarming. Instead of accelerating smoothly toward its theoretical top speed, the Spitfire began to vibrate with increasing intensity. At 370 miles per hour, the entire airframe shook so violently that Sterling could barely read his instruments. The contra-rotating propellers, designed to operate in perfect harmony, seemed to be creating destructive interference patterns that threatened to tear the aircraft apart. Boscom control test 27 experiencing severe vibration above 370 miles per hour. Sterling reported his voice tight with concentration as he reduced power to bring the shaking under control. I'm returning to base for emergency. Landing. The landing approach revealed another unexpected characteristic of the modified aircraft. With power reduced to idle, the Spitfire descended much more rapidly than normal, requiring constant power adjustments to maintain proper glide path. The additional weight and altered aerodynamic characteristics of the contra-rotating propeller system had fundamentally changed the aircraft's flight envelope in ways that Harrison's team hadn't fully anticipated. Sterling touched down at Bosom Down after 43 minutes of flight testing, his face grim with the knowledge that Harrison's revolutionary design had failed its first crucial test. The contra-rotating propellers worked as advertised in eliminating torque reaction, but they had introduced new problems that might prove even more dangerous than the original difficulties with the Griffin engine. As ground crews swarmed over the aircraft, checking for structural damage from the severe vibrations, Harrison approached Sterling with the expression of a man watching his life's work crumble. The test pilot's report would determine whether the contra-rotating propeller project continued or joined the long list of promising aviation innovations that never survived their first encounter with reality. The emergency meeting convened in Hangar 7 2 hours after Sterling's landing, with Harrison facing a circle of engineers, test pilots, and ministry officials whose expressions ranged from disappointment to barely concealed anger. The modified Spitfire sat silent behind them, its contra-rotating propellers now motionless, but still radiating an aura of mechanical menace. Air Commodore Palmer had driven down from London immediately upon receiving Lawrence's preliminary report, and his presence transformed what should have been a technical debriefing into something resembling a court-martial. Squadron Leader Sterling Palmer began, his voice carrying the weight of institutional authority. Please give us your complete assessment of the aircraft's performance characteristics during today's test flight. Sterling stood at attention, though his flight suit still bore sweat stains from wrestling with an aircraft that had nearly shaken itself apart. Sir, the contra-rotating propellers completely eliminated torque reaction during takeoff and low-speed flight. The aircraft tracked straight down the runway without rudder input, and handling below 300 miles per hour was exceptional, possibly the best I've experienced in any Spitfire variant. A murmur of surprise rippled through the assembled engineers. Despite the flight's dramatic conclusion, Sterling's initial assessment suggested that Harrison's basic concept had succeeded in solving the Griffin engine's primary problem. However, Sterling continued, his tone becoming more somber. Above 370 miles per hour, the aircraft experienced severe vibrations that made further speed increases impossible. The entire airframe shook so violently that I feared structural failure. Additionally, climb performance was significantly degraded. We required nearly full power to achieve climb rates that should have been possible at 75% throttle. Harrison felt the weight of failure settling on his shoulders like a lead blanket. 6 months of calculations, manufacturing precision, and professional reputation had produced an aircraft that performed brilliantly at low speeds, but became uncontrollable precisely when maximum performance was needed most. The irony was bitter. He had solved the torque problem only to create vibration issues that were potentially more dangerous than the original difficulties. Chief Engineer Lawrence consulted his clipboard of technical data, searching for explanations that might salvage something from the day's disaster. Our ground-running test showed harmonic vibrations at specific engine speeds, but nothing approaching the severity Squadron Leader Sterling experienced in flight. The aerodynamic loads at high speeds seemed to be exciting resonances in the propeller system that we didn't anticipate. Director Hughes leaned forward, his reputation for technical precision making his questions particularly pointed. Mr. Harrison, your original calculations presumably accounted for aerodynamic forces on the propeller assemblies. How do you explain this discrepancy between predicted and actual performance? Harrison had spent the past 2 hours analyzing the same question, and his answer revealed the fundamental challenge of aviation engineering during wartime. Sir, our calculations were based on static ground testing and wind tunnel data. The interaction between two contra-rotating propellers in actual flight conditions, particularly at high air speeds, creates aerodynamic phenomena that are extremely difficult to predict without actual flight testing. The propeller tip vortices appear to be creating destructive interference patterns that weren't apparent in our laboratory work. The explanation was technically accurate, but offered little comfort to officials who had invested months and considerable resources in Harrison's experimental design. Air Commodore Palmer's expression suggested that he was already calculating the political consequences of another failed aircraft modification program. The question now, Palmer said grimly, is whether these problems can be solved within a reasonable time frame, or whether we should abandon this approach entirely and focus on conventional solutions to the Griffin's torque issues. Harrison felt his career hanging in the balance, but his engineer's instincts refused to accept defeat without exploring every possible solution. Sir, I believe the vibration problems can be resolved through modifications to the propeller blade design and gearbox timing. The fundamental concept remains sound. We simply need to eliminate the aerodynamic interference that's causing the destructive resonance. Test pilot Sterling, despite having risked his life in the morning's flight, found himself unexpectedly supporting Harrison's position. With respect, sir, the aircraft's handling below 370 miles per hour was remarkable. If Mr. Harrison can solve the high-speed vibration issue, we could have an aircraft that combines the Griffin's power with handling characteristics that exceed any fighter currently in service. The room fell silent as the officials weighed the competing demands of technical perfectionism against operational urgency. Allied intelligence reports indicated that German aircraft manufacturers were rapidly developing new high-performance fighters. While the invasion of Western Europe, still months away, but already consuming enormous planning resources, would require absolute air superiority over the battlefield. Harrison seized the moment of uncertainty to present his proposed solution. The vibration analysis suggests that the problem lies in the relationship between propeller blade angles and rotational speeds. By adjusting the gear ratios to alter the speed differential between forward and rear propellers, we can shift the harmonic frequencies away from the critical resonance points. Additionally, modifying the blade twist distribution should reduce tip-vortex interaction. Lawrence looked up from his calculations with cautious optimism. The modifications Mr. Harrison describes would require approximately 3 weeks of machine shop work and another week for rebalancing the entire system. We could have the aircraft ready for second-phase testing by mid-March. Air Commodore Palmer consulted his pocket watch, clearly calculating timelines against competing priorities. The Ministry of Aircraft Production was under enormous pressure to deliver combat-ready aircraft, and every week spent on experimental modifications delayed the deployment of squadrons that might be desperately needed over Europe. Mr. Harrison Palmer said finally, "You have one more opportunity to prove your system, but understand that this represents the absolute limit of our patience with experimental approaches. If the second test flight fails to demonstrate clear improvements, we will abandon the contra-rotating propeller program entirely and focus our resources on conventional torque reduction methods." As the meeting dispersed, Harrison remained behind in the hangar, staring at the silent Spitfire that represented both his greatest technical achievement and his most humbling professional failure. The aircraft looked deceptively ordinary now. It's a revolutionary propeller system, just another piece of machinery awaiting modification. But Harrison's engineers could already visualize the changes needed to transform his partially successful experiment into the war-winning weapon he had originally envisioned. The next 3 weeks would determine whether Robert Harrison's stupid idea would revolutionize fighter aviation or become a cautionary tale about the dangers of challenging conventional wisdom during wartime. Either way, the fate of Britain's most famous fighter aircraft now depended on gear ratios, blade angles, and the complex physics of spinning propellers that most pilots never bothered to understand. In the gathering darkness of the February evening, Harrison began sketching modifications that would either vindicate his radical thinking or end his career in the aviation industry forever. The morning of March 18, 1944 brought clear skies and calm winds to Bosom Down. Conditions that seemed almost too perfect for what everyone understood would be the final test of Harrison's controversial propeller system. 3 weeks of intensive modifications had transformed the contra-rotating assembly into something that looked subtly different from its original configuration. Though the changes were invisible to anyone not intimately familiar with propeller blade geometry and gearbox ratios, Harrison had spent sleepless nights recalculating every aspect of the system, focusing particularly on the harmonic frequencies that had nearly destroyed the aircraft during its first flight test. The solution lay in altering the rotational speed relationship between the two propellers from the original 1825 and 1475 revolutions per minute to a new configuration of 1,700 and 500 revolutions per minute respectively. The closer speed differential would shift the critical resonance frequencies away from the aircraft's normal operating range while maintaining the torque-canceling effect that made the system valuable. Additionally, Harrison's team had modified the blade twist distribution on both propellers, reducing the aggressive angle changes near the tips that contributed to vortex formation. Each blade now featured a more gradual transition from root to tip, designed to minimize the aerodynamic interference that had created destructive vibrations at high speed. The modifications required hand finishing each blade to tolerances measured in thousandth of an inch, work that consumed 2 weeks of painstaking craftsmanship. Squadron leader Sterling approached the modified Spitfire with cautious optimism, tempered by vivid memories of his previous flight's violent conclusion. The aircraft looked identical from a distance, but close inspection revealed the subtle changes that might transform it from a dangerous experiment into a revolutionary weapon. The propeller blades caught the morning light differently. The revised geometry, creating shadow patterns that seemed somehow more purposeful than the original configuration. The gearbox modifications tested perfectly during ground running. Chief Engineer Lawrence reported, though his voice carried the tension of a man who understood that ground testing meant nothing until proven in actual flight conditions. We maintained stable operation through the entire power range without the harmonic vibrations that plagued the original system. Oil temperatures stayed within normal limits, and the new gear ratios eliminated the resonance frequencies we identified during failure analysis. Air Commodore Palmer had returned from London specifically to witness this second test, bringing with him a sense of institutional finality that affected everyone present. The Ministry of Aircraft Production could not afford to continue experimental programs indefinitely, particularly when conventional aircraft were desperately needed for the anticipated invasion of Europe. This flight would determine not only the fate of Harrison's propeller system, but potentially the future direction of British fighter development. At precisely 10:15, Sterling fired the Rolls-Royce Griffin engine and immediately noticed differences from the previous test. The sound was subtly different. Still the complex harmonic created by contra-rotating propellers, but somehow more controlled, less aggressive in its mechanical resonance. The engine instruments showed normal readings as he advanced power for taxi, and the aircraft tracked straight without the slight vibration that had characterized the original system, even during ground operations. Takeoff at 10:28 revealed the most dramatic improvement. Where the previous flight had required nearly full throttle to achieve acceptable climb performance, the modified aircraft now ascended at 2,000 feet per minute using only 80% power. The revised propeller geometry had apparently eliminated much of the aerodynamic inefficiency that had plagued the original design, allowing the Griffin engine's full power to translate into actual aircraft performance. Bosom Control Test 27 climbing through 8,000 feet, Sterling radioed his voice, carrying cautious excitement. Climb performance is significantly improved over the previous test. Handling characteristics remain excellent. Requesting clearance to test speed envelope. The response came immediately. Test 27. You're cleared for speed testing. Exercise extreme caution approaching previous problem areas. Sterling leveled the Spitfire at 10,000 feet and began his cautious exploration of the speed range that had nearly killed him 3 weeks earlier. At 300 miles per hour, the aircraft flew with the smooth precision he remembered from the best conventional Spitfires. At 350 miles per hour, still no unusual vibrations or handling anomalies. As the airspeed indicator crept past 370 miles per hour, the speed at which the original system had become uncontrollable, Sterling held his breath and waited for the violent shaking that had forced his emergency return. Instead, the Spitfire continued to accelerate smoothly. At 400 miles per hour, the aircraft felt more stable than most fighters at half that speed. The elimination of torque reaction combined with the resolved vibration issues had created something unprecedented in aviation. A high-powered fighter that actually became more controllable as it approached its maximum performance envelope. Bosom Control Test 27 has achieved 410 miles per hour with no adverse handling characteristics. Sterling reported, his voice now carrying genuine excitement rather than caution. The aircraft is completely stable and responsive. This is remarkable performance. From the control tower, Harrison watched through binoculars as his modified Spitfire carved precise turns against the blue Hampshire sky. The contra-rotating propellers transforming the massive power of the Griffin engine into speed and agility that seemed to defy the laws of aviation physics. The sight vindicated not only months of technical work, but his fundamental belief that conventional approaches were insufficient for the challenges of modern warfare. Sterling continued testing for another 25 minutes, exploring every aspect of the aircraft's performance envelope. High-speed dives revealed that the Spitfire could exceed 450 miles per hour in a controlled descent without developing the compressibility problems that affected many high-performance fighters. Tight turns at maximum power demonstrated handling that combined the agility of earlier Spitfire variants with the raw performance of the Griffin engine. Landing at 11:32, Sterling taxied to the hangar with the expression of a pilot who had just experienced something genuinely revolutionary. As he shut down the engine and climbed from the cockpit, his first words to the assembled engineers and officials carried the weight of professional expertise earned through years of combat flying. "Gentlemen," Sterling announced, removing his flying helmet and looking directly at Harrison. "What you have created is not simply an improved Spitfire. This is the finest fighter aircraft I have ever flown. The combination of speed, handling, and controllability exceeds anything in current service with any Air Force in the world." Air Commodore Palmer approached Harrison with an expression that had transformed from skeptical authority to grudging admiration. The successful test flight had validated not only the technical approach, but the strategic decision to pursue unconventional solutions to seemingly impossible problems. "Mr. Harrison," Palmer said formally, "I believe congratulations are in order. Your contra-rotating propeller system has exceeded our most optimistic performance predictions. The question now is how quickly we can begin production modifications for operational squadrons." As the small group of engineers and officials gathered around the modified Spitfire, Harrison felt the satisfaction of vindication tempered by awareness of the enormous challenges ahead. Proving that his system worked was only the beginning. Transforming experimental success into battlefield advantage would require manufacturing precision, pilot training, and logistical support on a scale that would test Britain's wartime industrial capacity to its limits. But for this moment, standing beside the aircraft that had transformed his radical idea into demonstrated reality, Harrison allowed himself to imagine Spitfires with contra-rotating propellers dominating the skies over Europe. Their impossible speed and agility providing the margin of superiority that could determine the outcome of the war itself.